Hello, my name is Safa, and today I'll be presenting forward some implications and applications of calculus. Starting with the applications of differentiation in economics, um, derivatives help us measure rates of change, optimize outcomes, and make predictions. In economics, this means analyzing things like cost, revenue, and profit functions. Let's dive into some practical examples. In economics, we use derivatives to calculate marginal cost, marginal revenue, and marginal profits. Starting with the cost function, which is C of x. What is C of x? C of x is the cost of producing x units. Now, x units is our input here. When discussing cost functions, we have to analyze our input, which is x units, the cost. If we input x here, this will give the cost of producing these x units. For example, I'm producing t-shirts. These are my item of production, and if I'm producing 100 t-shirts at a time, I'll be inputting 100 in this cost function to calculate what my uh, total cost of producing these t-shirts will be. Moving forward, where do we apply derivatives in these cost functions? We have marginal cost, which is MC. It is the cost incurred in producing an extra unit, given that X units have already been produced. So, how do we represent MC? MC, or the marginal cost, is the derivative of this cost function, which is C of X, with respect to X units. Moving forward, we have our revenue function, or R of X, which is the revenue from generating X units. Now we have to focus here that revenue is not our profit, it is just the total amount that we're bringing in for producing these X units. Marginal revenue, or MR, is the revenue earned in producing and selling an extra unit, given that X units have already been produced and sold. So, marginal revenue, or MR, is the derivative of this revenue function with respect to x. Revenue function, or R of x, can be calculated by the revenue generated by selling x unit at a price P. The price P may be fixed or it can vary. So, price P is equals to f of x, which is the highest price charged in order to sell x units. So moving forward, we have the profit function, which is P of X. Now, profit is the revenue that we bring in for producing or generating X units of our items, minus the cost that we put in for producing these X units. This is the profit, or probably in some cases loss that is generated by producing and selling X units. So, what is marginal profit? Marginal profit, or MP, is the profit gained by producing and selling an extra unit, given that X units have already been produced and sold. How do we represent the marginal profit? It is the derivative of the profit function with respect to X units. So here I've jotted down three cases, case A, B, and C, where case A is at maximum revenue, we have to solve dr by dx, which is the marginal revenue, and we have to equate it to zero. Now, if we recall, we used to equate our derivative equal to zero if we had to find the stationary points. Now, this is to solve for x. When we solve dr by dx is equals to 0, this we say is the revenue maximizing level of production. Now, to ensure or to test that our revenue generated is maximum, we can use the second derivative test, which is d square r over dx square. And if it's less than 0, that means the revenue maximizing level of production. Moving forward, the case B is at maximum profit, we have to solve dp by dx. dp by dx is our marginal profit. We have to equate it to 0 to find the maximum profit, and we can solve it to find x. Now, this we say is the profit maximum level of production. And again, to test it, or we use the second derivative test, which will be less than 0 for the level of production to be maximum. Now case C is minimum cost. We have to solve dc by dx, which is the marginal cost, and we equate it to 0 to solve for x. Again, we can test it by using the second derivative test, but in this case it has to be greater than 0 for the cost to be minimizing level of production. Moving forward, I have an example. The example says an office supply company sells X pens per year for $P per pen. The P is our price that we are going to charge per pen. The demand equation for these pens is given by P is equals to 10 minus 0.01 X. X is our variable. P is the price or the demand equation. The A part says what price should the company charge per pen in order to maximize revenue. I have highlighted the word maximize. Then what is the maximum revenue? Let's try to solve this question. Here we have our revenue as we implied before, that revenue is equals to x units into the multiplied by price, which is our total revenue. Here we have the demand or the price equation. We put it and multiplied by x to find the revenue equation. We get 10x minus 0.01 x squared. We differentiate the equation for to find the marginal revenue. Differentiating the equation gives us 10 minus 0.002x. And as implied before, to find maximum, we equate our derivative equals to 0. As we equate it to 0, we get 5,000, which is our x, or the maximum number of pens sold per year. Now, to make sure that 5,000 is the maximum number that can be produced per year, we can do a simple derivative test. Here we have 5,000. If, for example, I equate 0 in this revenue equation, which is 10 minus 0.02x is equals to 0. If I equate 0 in place of x, I would get positive answer. And if I equate, let's say, greater than 5,000, let's say I equate 10,000 in this equation, I would get a negative answer, which proves that 5,000 is our maximum number of pens sold per year. And now the second part asks, what is the maximum revenue? To find revenue, we have to find the price that is charged per pen. Just using our demand equation from before, the original equation, we equate 5,000 in the equation and we get $5 per pen to be charged. Now the maximum revenue generated is 10x minus 0.001x squared, equating 5,000, we get $25,000, which is our maximum revenue generated. Now part B asks here, if the cost function is C of x is equals to 5,000 plus 2x, what is company's maximum profit? What should the company charge per pen and how many pens should be produced? Here we have our profit equation. As we implied before, profit is equals to revenue minus cost. So our revenue function that we calculated, that we found from here, is 10x minus 0.01x squared and minus our cost equation, which is 5,000 plus 2x. This gives us the profit equation. Now differentiating the profit equation would give us the marginal profit, which is minus 0.02x plus 8. As implied before, to find the maximum profit, we equate it to 0 and we get 4,000 pence. Now, this is different than what we found before, which was 5,000 maximum pens sold per year. Just to make sure that this 4,000 pens is actually the maximum number of pens which can be generated to produce the maximum profit, which is asked in the question. Just a simple derivative test and we can prove that 4,000 is actually the maximum. Inputting 4,000 in our price equation, we get 11,000 for our profit. $11,000 is our profit. So price P to be charged per pen in order to maximize the profit would be $6 per pen. For example number 2, in marketing a certain item, a business has found that the demand for the item is represented as the function P is equals to 55 over under root X. The cost of producing X items is, now we are given the cost function which is C of X is equals to 0.4X plus 700. Find the price per unit that gives the maximum profit. Here again we are asked for the maximum profit. This is very easy. We have our we have our cost function, we have our price, we can make out an equation for our profit. Just to be sure, we as we have already deduced before that revenue is the price multiplied by x units, we have the price equation which is 55 over under root x. We multiply it with x units and our revenue is 55 times x under root. Just putting it back into our profit equation, 55 under root x minus 0.54x plus 700. This is our profit equation. To find the maximum profit, we have to find the marginal profit, which is differentiating the profit equation, the profit function. Differentiating it gives us 55 over 200x minus zero point 0.4. To find the maximum profit, we have to equate the marginal profit equals to 0, and this gives us under root 68.75. Now putting it back into our demand equation, we can deduce that we have to charge $0.80 or 80 cents per item that we're producing to maximize the profit. Moving forward to example 3, a manufacturer knows that the profit from selling X units of a certain item is given by the function P is equals to 0.003x cubed plus 9x. Now we are given the profit function. Find the marginal profit of the production level of 81 units. Find the actual gain in profit by increasing production from 81 to 82 units. We are given our profit function. We have to find the marginal profit of the production level of 81 units. We just differentiate our profit equation to find the marginal profit. We have the equation of marginal profit. Now they're asking the production level of 81 units. We input 81 into our marginal profit or our differentiated equation, which gives us 14.9049. Find the actual gain in profit by increasing production from 81 to 82 units. Now, the actual gain in profit has to be calculated by inputting the values in our original profit equation. We input 82 minus 81, and this is the actual gain in profit, which is 14.98. So, moving forward, we have the washer method. First, let's understand what we mean by a washer. A washer is essentially a disc with a hole in the center. The washer method is a modification of the disk method where the volume of a solid formed by revolving around an axis when the cross section is a solid disk is calculated. So we know the disk method where we had to calculate the volume of a solid by revolving it along an axis, and the cross section when the cross section is a solid disk. Now here we had a solid disk, but in the washer method, instead of solid disk, the cross section of the solid are washers, rings, or a solid with a hole in the center with an outer radius and an inner radius. When do we use the washer method? If the axis of revolution is not a boundary of the plane region and the cross sections are taken perpendicular to the axis of revolution, then the washer method can be used to calculate the area of the solid. For, here we have this test. This is our washer with the void inside. This is our d of x, which is perpendicular to the axis of revolution. So the area which is bounded by this region, this shaded region, will be pi fx square minus pi g of x square, or simply said, the area of the upper curve minus the area of the lower curve. F of x is the upper curve while g of x is the lower curve. Now, What we studied before is that volume is equals to area into depth. Now this is the volume for one washer, which is one revolution here drawn in this diagram. For for calculating the volume of this whole region of by rotating this whole region, we would have to take an interval from A to B, from this point of intersection to this point of intersection of the both graphs. So here we can imply that volume is equals to pi from A to B, our interval fx square minus g of x square into dx, which is our depth. Now this is our depth. Moving forward, I have an example here. Our example says find the volume of the solid form by revolving the region bounded by the graphs of y under root x minus 1 and x minus 1 square about the y axis. We have to revolve it around the y axis. Our y1, our first graph is under root x minus 1, our second graph is x minus 1 whole square. Here I've drawn it. This is our y x minus 1 square, and this is our under root graph. So if we draw it, the shaded region here is the region which we have to calculate the volume of when it is revolved around the y-axis. This is our interval A to B, the points of intersection. To find the point of intersections A and B, we have to rewrite our equations in terms of y. We have to make x the subject here. Our first equation would be under root y plus 1 is equals to x, while the second would be y squared plus 1 is equals to x. To find the points of intersection, we have to equate x equals to x. This gives us two values for y, 0 and 1. We know for sure that a is 0 and b is 1, our second point of intersection. Now we use the washer method. We have already derived the formula. The formula is v is equals to pi a to b integral of y1 square minus y2 square, or simply said, the integral of the upper curve minus the integral of the lower curve. We input our equations, we put our bounds, which is 0 to 1, and this gives us solving it, calculating the integrals and calculating the bounds, give us the final volume, which is 29 pi by 30. Moving forward, I have moments and center of masses. So let's look how moments and center of masses go together. What is moment? It is the measurement of a force's tendency to cause an object to rotate about a specific point or axis. We represent moment with this uppercase m, which so moment is equals to m, which is the mass of the object, into d, the distance from the axis of rotation. I have given a diagram here just to explain it. Here we have a fulcrum. This is a type of a seesaw. We all have ridden a seesaw when we were kids. So we can just use the example of a seesaw to understand moment. Here I have a fulcrum here. I have my mass m1 and my mass m2. Now, the d distance from the fulcrum to m1 is d1, and the distance d2 from m2 to our fulcrum is this. So our moment will be m1 and d1, and our second moment will be m2 and d2. This will imply that our total moment is m1 d1 plus m2 d2. Now, what is center of mass? It is the point where the mass of a system or object is balanced in all directions. Now, this x dash is our center of mass, which means that our the system, or this seesaw, whatever you want to call it, it is balanced at this point, or this is our center of mass. This is a one-dimensional system. Now this implies that the x, or a center of mass, is sum of moments over total mass. So here I have this diagram where I have an x-axis and a y-axis. This red dot here is my mass, the distance yi and the distance xi. we'll be using yi and xi to calculate moment along x-axis will be mx, which is mass m into yi. Moment along y-axis my would be mass into xi. As we have already implied what center of mass is, so we'll be calculating center of mass x slab is equals to moment along y-axis over total mass, and center of mass for y will be rotating this way, which is moment along x over total mass. And this xi, yi, x slab and y slab will be our center of mass. Here I have a simple example. Find the center of mass for the following system with point masses m1 or mass 1 is equals to 7 and m2 or mass 2 is equals to 3, located at 1, 2 and 3, 4 respectively. Here I have drawn a graph and represented it. This is our m1, which is located at x1 and y2. This is our m2, which is located at x3 and y4. Now we'll calculate our center of mass along x-axis, which is m1 x1 plus m2 x2 over m1 plus m2. This is our total moments along the x-axis over our total mass. This gives us 1.6. Now we'll be calculating the center of mass along y-axis, m1 y1 plus m2 y2, which is our total moment along y-axis over m1 plus m2. This gives us 2.6. And this is our center of mass for this two-dimensional system right here, x dash and y dash, which is 1.6 and 2.6. This marks the end of my presentation. Thank you very much.